Thank you very much. First, I would like to thank the organizers for giving me an opportunity to speak here. Just a small correction. My name is Mousami Bhakta. So this is not bhakta. It's not anyway, doesn't matter though. No. So I start the talk. So this is the plan of the talk. So I will talk about the classical Sobolev inequality in the Euclidean space, and then I will explain what is stability for Sobolev inequality, and then next topic will be I will introduce what is Poincare-Sobolev inequality in the hyperbolic space, and then I will discuss about stability of Poincare-Sobolev inequality. So this is the classical Sobolev inequality, which many of us are used to, very much familiar with this. So this says that if we take any C infinity function, a class of C infinity function with compact support, then we can control the L2 star norm. 2 star is 2n by n minus 2. N is the dimension of the Euclidean space. So we can control the L2 star norm by the L2 norm of the gradient. So this is the classical Sobolev inequality. And what's special about here is this constant SRn. So let me see. Yeah. Just a second. Yeah. So this constant SRn, so this just depends on the dimension. This just depends on Rn. Okay. So it doesn't vary with the function. And now is using the density result. This inequality, Sobolev inequality, classical Sobolev inequality, this holds for all the D12 function. So what is D12 function? That means that if you take this closure of C infinity function with the compact support for closure of C infinity C, this is the C infinity function. If you take the closure of this function with respect to the this norm, so this will be norm square. This is the norm square. If we complete this space with respect to this norm square, then this space we call D12 space. So like this Sobolev inequality holds for all these functions for which this L2 norm of the gradient is finite. Okay, this is the classical Sobolev inequality. Now you can ask that first. The question is that what is the special about this 2 star which I wrote 2n by n minus 2. So this just can be seen easily from the scaling factor, because if you like to have the Sobolev inequality, like if you want to control the any LP norm by the L2 norm of the gradient, and if you want this constant C to be independent of that function, then you can easily see that if you solve if this such inequality is true for U, then you can just put a parameter lambda and you put it U lambda x equal to U of lambda x. Then for U lambda x also it must be true. And then if we do the simple change of variable, then this must be true, right? If this inequality is true, Sobolev inequality. But then you can easily see that this exponent must be 0. Otherwise, if it is not 0, if this one n minus 2 by 2 strictly greater than n by p, then taking lambda goes to infinity, this will blow up the left hand side. And if this is n minus 2 by 2 strictly less than n by p, then if taking lambda goes to 0, then again this will blow up. So only possibility, if at all such inequality is true, then this must be 0, and which will imply that p has to be 2 stars. So that's why this 2 star coming in business. Now, what are some feature of this inequality? So one main feature is that this inequality is preserved if we just change a function. Suppose U is optimizer for this one. For U this inequality becomes the equality. Then what you can do is that if you just change U by the scaling, by this dilation and the translation, then again the inequality will be the same. Because the norm will not be changed. So this is if the transformation, which is actually a dilation, and this is translation, and this part is the dilation. So Sobolev inequality is invariant under this conformal changes. Okay, and the best constant is Sobolev, this SRn, this is well known already, and it has been studied. Now, this Sobolev constant, you can characterize it. This is easily you can just write it from the Sobolev inequality part. So this is the Sobolev inequality part. So you can just write SRn is less than equal to this right hand side part divided by this this part, right? That is less than equal to. So if you take infimum over all these functions and with u not equal to 0, that's the Sobolev constant. This. So it has been and it has been already proved that the Sobolev constant is achieved by over-Talenti bubble, and this is actually achieved if and only if this u is actually constant multiple of this over-Talenti bubble. So this is over-Talenti bubble. So this uz mu is defined exactly the way here we have defined. This is the scale dilation and the translation. Okay, and what is ux here? Capital Ux. This is the function. This is so-called over-Talenti bubble. So they have actually first proved that the Sobolev constant is achieved by this function. Okay, so I mean, if for any if you find any optimizer for the Sobolev inequality, it must be the translation, dilation, or the constant multiple of this function. Now, from here, what we can observe is that the set of the equality set cases for the Sobolev inequality, I mean, for we are interested the extremal functions for which the Sobolev inequality becomes the equality. So that actually the extremal functions, they form the n plus 2 dimensional manifold in D1 to Rn. So this n plus 2, roughly you can just see it from here, because there are, you see here this z is in running in Rn, so you get it in n dimension. Mu is 1 dimension scalar, and then there is a constant. So from here you can just get the idea that from where this n plus 2 is coming in picture. Okay. Now, and there is a constant you can see here. This constant is so this constant has been chosen in such a way that that capital U, this actually this is the over-Talenti bubble capital U. This
no, we can't hear you sometimes.
Oh, I'm sorry. Can you hear it now?
Yeah, and there's some noise coming from the.
I don't know.
No, now it's fine. Now it's clear.
Okay. So let me put it more closer to me. Okay. So that dimensional constant here actually ensures that U is a positive solution of this Euler-Lagrange equation. Okay. So now let me explain what do I mean by the stability of Sobolev inequality. So you see that given any function, if we start with any function in this D1 to space, we can actually define deficit in the Sobolev inequality by this functional. So you see what is this is functional. So this is actually by Sobolev inequality, this is, we know that this is greater than equal to 0, right? And if if U is an extremal for the Sobolev inequality, I mean, if U achieves the Sobolev inequality, then this must be 0. So now del phi is, we are just taking everything on the right hand side, and that we are defining as the deficit functional. Now, in 1985, Brzezinski posed this question: can we actually bound this deficit functional from below? This is the question. Can we bound this from below by the distance function, of U from the manifold M? So M is the set of all extremal functions for the Sobolev inequality. So question is that can we bound it from below from by the distance function of U to M, by the distance from U to M? Okay. Or in other words, I mean, this is the question, or you can also ask another question, that if U almost optimizes the Sobolev inequality, then is U close to the set of extremals? That's another way you can ask this question. So this distance function, since we can define it in this way, because this is the in D1 to space, this could with the gradient L2 norm of the gradient, this is the natural way you define the distance function. Okay, and in 1991, Bianchi-Agnel answered this question assertively, and they have proved that this is indeed true, and there is a linear stability. So they have proved that this deficit functional can be bound, controls actually the distance of phi from the manifold. So that means that if a function phi almost optimizes the Sobolev inequality, then it is actually close to the a set of extremal function. Okay, then it is almost close to an extremal. Now, this question of stability of several well-known, the question of stability for several well-known inequality, for example, isoperimetric inequality, log-Sobolev inequality, Gagliardini-Sobolev inequality. There are many anisotropic Sobolev inequality. There are many inequality. For that, this has been well studied, and here are some of the references. And you can see that some of the references are quite very recent. For example, this is coming in 2023, and there are quite many application to this because of this, and it's a very hot topic these days. Now I introduce what is Poincare-Sobolev inequality in the hyperbolic space. So before starting with inequality, so what is the hyperbolic space? So here I will talk about the hyperbolic space of ball, ball model of the hyperbolic space. So what do I mean by that? So we start with the Euclidean ball. Euclidean unit ball, you take it mod x less than 1, but instead of Euclidean metric, I put a different metric. So this is the metric we are talking about here. So this is 2 by 1 minus mod x squared whole square times Euclidean metric. So ball with unit ball with respect to this metric is called the ball model of the hyperbolic space. Okay, so with this metric, this boundaries of this ball becomes actually the infinity there. So and so here this is the volume element will be given by this one. Now there is a Poincare-Sobolev inequality in this space, which states that if you have dimension greater than equal to 3 and lambda is less than equal to n minus 1 by 2 whole square, P is strictly greater than 1 less than equal to 2 star minus 1. 2 star is the same 2 star, 2n by n minus 2. Then there exists a best Sobolev constant such that this inequality holds for every u in CC infinity Bn. So Bn is the ball. So now what is this n minus 1 by 2 whole square? That is the bottom of the spectrum for the Laplace-Beltrami operator in this space. And since we are in strictly, we will be actually interested in lambda strictly less than n minus 1 by 2 whole square. And in that case, this will become an equivalent norm for norm u lambda square. So this becomes a norm, and this will become an equivalent norm for H1Bn space. So that is H1Bn means this is a function is in H1Bn if u is in L2 and its derivative is also in L2. That's H1Bn space. So this is Poincare-Sobolev inequality. So now here again, question is that when this inequality is achieved, and achieved by which function? These are the first question before talking about the stability. So in 2008, Mancini-Sandeep have completely characterizes the extremal functions for this Poincare-Sobolev inequality. So here we have this assumption here, because in these cases only the existence and uniqueness of the solution is there. Other complement, there is no, in fact, non-existence of the solution will be there. So when you are in the critical, when you are in the subcritical case, n greater than equal to 3, then lambda is less than n minus 1 by 2 whole square. And when in the critical case, n greater than equal to 4, then lambda is lying in this range. Okay, so in that case, they have proved that there exists a unique extremal for the unique radially extremal function for the Poincare-Sobolev inequality. Unique in the sense of that it is unique up to the hyperbolic translation. Okay, so that means if u is a solution and if xi is any point in Bn, so if you define tau xi is the hyperbolic translation, then u composed with tau xi will be the solution. So unique up to this, and this unique solution is positive, radially symmetric, and radially decreasing. So now here again we can the next talk about the stability of the Poincare-Sobolev inequality. So since because of thanks to the result of Mancini-Sandeep, here again we can talk about the set of the extremal functions, and the set of the extremal functions here again, and from an n plus here they form the n plus 1 dimensional manifold. So and why this again, why it is n plus 1, that can be actually seen from this xi is n, and you will get here constant which is 1. So n plus 1 dimensional manifold Z0. So again we define the deficit functional here the way we defined for the Sobolev inequality. So del u we defined it. So this is exactly the Poincare-Sobolev inequality. You take it everything on the left hand side and just we put the power. So this is the deficit functional. We define it here. Okay, and correspondingly we define the manifold. We define the distance function from the manifold, which is with usual a definition of the a distance function in that space in H1Bn. Okay, so you are taking the u minus the any element, and you are taking the you are minimizing over that function. So this is the one. Okay, so in a recent work with Devdeep Ganguly, Debabrata Karmakar, and Shoikat Majumdar, we have proved that here again we have this linear stability. That means if you almost optimizes the Poincare-Sobolev inequality, then actually U is close to this extremal. But this is not just a linear stability. What we have proved here, this linear stability is more than what just now I stated, because it, I mean, this one, this linear stability implies what just I said, but this is more stronger. So it just says that you can bound this deficit functional from below by the distance function of U to the manifold. Just a second, what happened? Oops. Okay, so now correspondingly Euler-Lagrange equation, we can talk about the Euler-Lagrange equation corresponding to the Poincare-Sobolev inequality. So the Euler-Lagrange equation corresponding to the Poincare-Sobolev inequality will be of this form: minus Laplace Bn u, this is the Laplace Beltrami operator on the hyperbolic space, minus lambda u equal to u to the power mod u to the power p minus 1 u, u is in H1Bn. And we can define corresponding the energy functional. So the I lambda u is the energy functional corresponding to this Poincare-Sobolev equation. That means if we take the critical points for this energy functional, that will be a solution for this Euler-Lagrange equation. And we capital capital U, we denote by this capital U, we denote the extremal function, one unique extremal function, unique up to the translation, hyperbolic translation, that this U is positive, radially symmetric, decreasing, and this is the norm of this one and the corresponding energy. So the naive question one can ask that if a non-negative function U almost solves the above equation. So just what just we talked about, that was stability from the inequality point of view. Now we are asking the question stability from the Euler-Lagrange point of view, equation point of view. So question is that if a non-negative function U almost solve the above equation, then is U close to an extremal of the inequality extremal function that U compose tau xi for some xi. So that's the because we know that this is a unique solution for this Poincare-Sobolev equation. So question is that if a function almost solves the equation, is it close to this one? So what do I mean by almost solve? Almost solve means if we can consider this. Okay, so almost solved means, I mean that if you take every for the equation, you just take the Laplacian Bn u plus lambda u plus u to the power p minus 1 u. This h minus 1 norm, this is very small, this goes to 0. So that means almost solved or approximately solves. So the answer is generally false unless we put some extra hypothesis on it, and we can see it from here. So if you just define U equal to uz1 plus uz2, so what is uz1? The notation is this one. uz1 means U composed with the hyperbolic translation tau z1. Okay, so I didn't say that tau z is a hyperbolic translation which actually takes 0 to z. Okay, so it's a hyperbolic translation. It's an isometry in ball. Okay, so you take uz1 and uz2, summation of uz1 and uz2, and this z1 and z2 you are choosing in such a way that they are very far away from each other. So like this is your ball, you choose one here, another here z1 and here z2, and they are very far away because this is a in a ball with the metric we are talking about, their distance is quite big. So in that case, so this small u will solve this equation almost solve this equation, but you can see that this is not close to any one of this bubble. And how do you see that this almost solved this equation? Because you just put it here, so that will be then you get this kind of one term, right? And that is exactly integral uz1 to the power p minus 1 uz2, which that is the actually bubble interaction. And in our in our very recent work, we just showed that this bubble interaction is can be computed as this one. Okay, so it has exponential decay. So like when Z1 and Z2 are quite far away, then this is actually small enough. This term is actually small enough. So that will make that UZ1 plus UZ2 almost solve the equation. Okay. So now we saw that in general, the answer is not true. So now the question is, then can we say that the U is close to sum of hyperbolic bubble? Then again, the answer it will be in general not true, because there are example of non-trivial sign changing solution, which are not at all sum of hyperbolic bubbles. So actually in 2012, with a joint work with my supervisor Sandeep, when it was during my PhD, that time we have proved that if UN is a positive sequence of functions which almost solve Poincare-Sobolev equation, then in H1 norm, it is close to a finite sum of hyperbolic bubbles and localized Oberth bubble. So this is the Oberth bubble is the bubble that we that is the extremal for the Sobolev inequality, and here we are taking the localized. And what do I mean by hyperbolic bubble? So hyperbolic bubble is this capital U, which actually is the unique solution for the Poincare-Sobolev inequality. And we have shown that when P is subcritical, there are only hyperbolic bubble, and when P is critical, there are hyperbolic bubble as well as there can be hyperbolic bubble as well as localized Oberth bubble. So in this recent works, we have shown that. So if we take a sequence of non-negative functions, is almost solve Poincare-Sobolev inequality, and energy is and its energy is close to the energy of one single hyperbolic bubble. This is the energy of one single hyperbolic bubble. Then we have the linear stability result holds. That means if it is almost solved this one equation, Poincare-Sobolev equation, this goes to 0, then we have that we can from below we can bound it by distance of that function from the manifold. So this Z, and Z is the unique solution for the Poincare-Sobolev equation. So this generalizes the linear stability result of Siralov-Figali-Magin from the Euclidean case to the hyperbolic case. And then the last one I want to mention is the multi-bubble case. What happens in the multi-bubble case? So here it is the single bubble case. So one bubble it is we are talking about. So next question happens, because in the decomposition result we have shown that if we take a non-negative sequence of a function which almost solve Poincare-Sobolev equation, then in H1 norm it is close to sum of hyperbolic bubble and sum of it can be sum of hyperbolic bubble and sum of Oberth bubble, localized Oberth bubble. So the next theorem, what we have shown that if, in this range, if we take in the subcritical case there are only hyperbolic bubbles, but if we take the critical case there are Oberth bubble. But we have found a countable set capital lambda, which is a subset of this one. So if we just remove that countable set and then we take lambda in from that complement, then there is no Oberth bubble in the decomposition. That means if we take the energy of the functional, which is positive integer times the so this is the circle one is the energy of one hyperbolic bubble. So you just take the n number of n times of that. That means if you take a sequence which is close to n number of hyperbolic bubble, energy of close to n number of hyperbolic bubble, then this is actually sum of only n number of hyperbolic bubbles. Okay. So now in that case, question is that can we have the linear stability? And the answer is yes. That's what we've shown that if we take a non-negative sequence, of functions, if we take a non-negative sequence of function, it's almost actually solves the Poincare-Sobolev equation, and we have here this result stability multi-bubble case stability result holds for p greater than 2 actually, and the energy and lambda we are restricting in that case. In the critical case, where lambda is in the restricting in the set that we were just removing a countable set, then and this means that the energy, I mean, it is close to n number of hyperbolic bubble. Then we have this linear stability result holds. So this result generalizes the stability result of Figali-Glaudo in 2020 from Euclidean case to the hyperbolic manifold. So next is what about the case P less than equal to 2? So we have just shown that in this case, when P less than equal to 2, this linear stability result fails. So P less than, and if it is critical, P is equal to 2 star minus 1, then P less than equal to 2 means N greater than equal to 6. And that's why here we had this, the other one. So in this case, the linear stability result fails. So linear stability result fails doesn't mean that the stability result fails. So, I mean, there may be some non-linear stability, which we are still trying to explore it. So these are the references. Both of them are just submitted work, very recent submitted work. And here I stop. Thank you very much.
Thank you, Mousami. Any questions? Yes.
Shall I stop sharing the screen or?
No, maybe some slides may be
okay.
Yeah.
Hello. Yeah, I have some simple questions only. So in the initial slides, you said about that the Sobolev inequality is invariant under translations and dilations, right? So is it true for Poincare inequality as well?
Poincare inequality is invariant under the hyperbolic translation. So here, you do not have anything like dilation. So they are the conformal, any equivalent thing for the dilation. So here we have the isometry is Poincare-Sobolev when you are in the hyperbolic space, the isometry here, it is only the translation, hyperbolic translation. So here you have only invariant under the hyperbolic translation, and that's why I was saying that this is the when you are talking about this extremal, this unique up to the hyperbolic translation. So if U is a solution, unique solution, you use the unique solution up to the hyperbolic translation. So U composed with tau psi is a translation. So tau psi is isometric in the ball. So so you can now ask that what is the isometry, if you are not aware of what is the isometry group in ball. Yeah. So isometry group in ball is actually nothing but the finite composition of how should I say, finite composition of actually reflection with respect to sphere which is orthogonal to Sn minus 1. So this tau psi is actually an isometry. This is a hyperbolic translation which takes 0 to xi. And so if U is a solution then of Poincare-Sobolev equation, then U compose tau psi is a solution of Poincare-Sobolev equation. Or U is a extremal, then U compose tau psi is a extremal, because that is invariant under this hyperbolic translation.
Okay, and one more thing, when you define delta phi in the initial slides, you said that there was a question that whether we can find a lower bound, right? So yeah. Why are we interested for finding this lower bound? Is it to find the class, like the weak solutions via the method of calculus of variations?
No. So this has a very deep application in many cases. So this is called stability actually. So lower bound, I mean, so stability is one thing that can we, if something is close to the, I mean, something is very close to the Poincare-Sobolev. So see, delta phi is what? If delta phi is very small, that means that you almost optimizes the Poincare-Sobolev inequality or Sobolev inequality, right? So the question is that if it something almost solves Sobolev inequality, then is it actually very close to the unique solution? That's the question. And what is the application? It has actually application in many places. One of that I can immediately say is that fast diffusion equation. So what is, are you aware of what is fast diffusion equation?
No, actually.
No problem. So this is, see, this is, you must be knowing what is heat equation. So I can just write you quickly. So ut minus Laplacian u equal to 0. This is the heat equation, right? That you are, you are aware of.
Yeah.
So now I put it here. Oh, just a second. Yeah. So now I write here ut minus Laplacian of um equal to 0. Okay. So suppose I am in the Poincare-Sobolev case, so in Bn cross 0t and u equal to 0, u naught in Bn cross t equal to 0. Okay. So this is the, so m equal to 1 is the heat equation. Now when m less than 1, then it is the first diffusion equation. Okay, m greater than 1, you get the entropy equation. So in m less than 1, so there is then the what can actually I mean the existence, uniqueness of solution, smoothing effect of solution is everything is there. Okay, now the question is that when it is m less than 1, it is the first diffusion equation. Then that's a solution actually. Why it is called first diffusion equation? So there is a capital T you can find. After some time, capital T, it just becomes 0. Before that it is positive, and then it just becomes 0. Now question, what happens at I mean near T when it becomes 0? So the asymptote, if people are interested actually what happens to the asymptotic profile of the solution at near T. So now if you are interested in the asymptotic, studying the asymptotic profile of the solution near T, then this stability result plays a role to prove that what is the asymptotic profile, what is the rate of convergence there. So to prove that those things establish, this has a huge application in physics. So, and that to prove that you need this stability result.
Okay. Okay, thank you.
Okay.
Any other questions? I have one question. So you talked about Sobolev best constant, right?
Yes.
So given a manifold, can you find this Sobolev best constant in terms of geometry or something, like geometric quantity, or?
It is a geometric quantity, so it's not that, I mean, actually, it is actually a manifold property, that it's not that all the manifold will admit this Sobolev inequality. So the question is that there is a large class of manifold where we have these Sobolev inequality holds. Okay, so I mean, like Poincare-Sobolev inequality. So there are there are large class of manifold where the Poincare inequality holds. So, for example, here this, I mean, if it this Poincare, here I talk about this Poincare-Sobolev inequality also. So here I just talked about hyperbolic space where we have this Poincare-Sobolev inequality. It's not just only a hyperbolic space. In fact, in a big, I mean, Cartan-Hadamard manifold is an example where you have this Poincare-Sobolev inequality is there actually.
And the Sobolev constant is related to the geometry in some sense?
It is related to the geometry. It is actually. So this is actually the Sobolev constant here. You see that it is depending only the dimension Rn, and if we just you can actually also instead of whole Rn, you can also talk about the bounded domain. But in the bound, I mean, you can check that this is independent of that. I mean, I mean, for omega-1, omega-2, if you just take it, I mean, it is independent, and this is achieved only for this Rn. Okay? So it is a quite a geometric thing.
I see. And S of Rn is what? Sorry, can I ask?
S of Rn is the Sobolev constant. That is the
Okay.
So S of Rn is the Sobolev constant. This is
okay.
So this is the Sobolev constant. So this I mean, you take any function for which this norm, I mean, you can define this norm. That's what I was just saying. CC infinity function in particular, this the same constant holds for that.
Okay. Any other questions? Okay, thank you so much. Thanks, Mousami.
Thank you very much for the opportunity. Thanks.